Okay, good morning. So what I plan to do, I was asked to give a more elaborate talk. And since most of you are not yet mathematicians, I propose to start very slowly with something very, very elementary. And I hope all of you can follow a good part of the talk. And then afterwards, maybe it will be going faster, but I hope you can take something from the talk. Okay, so the title is The Lorentz Attractor. Let me begin by the story of Mr. Lorentz. Mr. Lorentz was a fantastic man. He died 2 months ago, and in 1962 he wrote a wonderful paper on determinism in physics, in meteorology. You must know that he was somehow a mathematician, because as a young student he began his studies as a math student, and he went to the World War II army, and during the war he was working on prediction of weather. And when he came back home, he was not a mathematician anymore, he was a physicist. So all of his life he was a meteorologist, but half mathematician, half physicist, and this is what I love. I mean, his papers, I will try to convince you that he's the right kind of scientist, mixing ideas from physics and mixing ideas from mathematics. Anyway, so in 1962 he was studying a very, very complicated problem called the convection in the atmosphere. You have the atmosphere, and on the bottom the air is hot, and on the top it's cold. So the hot part of the air has a tendency to go up, but when it goes up it gets colder, so it wants to come back down. And so you have a complicated phenomenon of some forces pushing towards the top, and some forces going down. So it's a very complicated mixture that even today we don't quite understand. Anyway, he was studying this problem, which is still a very active question today, and he made oversimplification. He took the partial differential equation, the Navier-Stokes differential equation, and he simplified it so much that it is completely clear that the simplification has little to do with the original question. He simplified it so much that he reduced it to a differential equation in 3 variables. Instead of dealing with something infinite dimensional like a partial differential equation is, he just reduced it to 3 poor variables, x, y, and z. And don't ask me what x and y and z are, because I don't even know. I mean, maybe x is pressure or something like that, but it is clear that even Lorentz doesn't know what the x, y, and z are. He just took the equation coming from physics and he just simplified it as much as he could in such a way that he could get something interesting. And then when he solved, this is very simple differential equation. It's a polynomial differential equation in 3 variables. And he solved numerically the differential equation with his very simple computer at the time, in 1962. The computers were very, very naive. And what he saw on his computer, or what he could have seen if he had such a Macintosh, he saw the following. He saw the behavior of the solutions looked completely crazy. If you pick a point as an initial condition x, y, z, and if you look at the trajectory starting from that point, you see a trajectory which is winding in space on this complicated object that looks like a butterfly, and going sometimes on the right, sometimes on the left, and you don't quite know if it's going left or right. So he was amazed to realize that such a deterministic system, which is a simple equation, could behave as if it were random. It's one of the first times where mathematicians realized that deterministic dynamical systems might behave as if they were random systems.
That's the first.
No, that's next slide. No, of course not. Okay, I know that. Okay. That's a very interesting question. He mentioned this phenomenon that we call today sensitivity to initial conditions, that you can see here, that if you take 2 points and you, with a very small distance apart, after a finite time they look very far apart. That's the main idea. Small perturbance implies big change. Of course, I'll come back to the history of that later on. Actually, let me tell you the truth. Yesterday night, when I prepared my talk, I had put maybe 10 or 15 transparencies on the history of that Hadamard and Poincaré and whatever, all these historical parts I like, but I had to cut it down. But I'll say something. So he realized that. Now, what is important in Lorentz's work is that he asked himself the following question. I took a physical question, I simplified it, I see some phenomenon. Does that apply to the actual initial problem I had in mind? This is a fascinating question. Is there a sensitive dependence on initial conditions on the weather? This is a very fascinating question that we could discuss for years. Anyway, to convince you that Lorentz is really a great man, he had the idea that in order to justify his computations, maybe it would be nice to have an actual physical problem behaving exactly like the equation in 3 variables that he had. So let me give you one example that I like. You can find that on the net. It's a very simple experiment that you can do yourself. So it's a bucket, it's a yellow bucket full of water, and the water is falling down this bicycle wheel, and around the bicycle wheels you have coffee cups, but these coffee cups have little holes on the bottom. So the water is falling inside the cups, and at the same time it's falling down from the cups. And you see that if you look at the behavior of the bicycle wheel, it's behaving completely randomly. And it's a good exercise for you to try to modelize, to write the equation for this simple mechanical system, and you will see that it is governed by the Lorentz equation. It's not anymore a partial differential equation, now it's an ordinary differential equation, and Lorentz, in his first paper, described the behavior of this bicycle wheel and showed that some physical kind of natural phenomena do occur randomly. So this is one of the reasons why I do have an infinite respect for him, that at the same time he's behaving like a mathematician and also as a physicist. Always he tries to make experiments checking his point of views on real, actual phenomena. And then I just want to show you a few pictures from his paper, just to show you that he understood everything much before mathematicians. Look at these pictures. These pictures, you can find them in mathematical papers 10 or 15 years later. For example, the picture on the right that I will discuss later is called the Williams template. We will discuss that in a moment. The Williams template has been introduced 10 years after this picture. And when I discussed that with Williams himself, I asked him why he was not aware of that. He told me Well, Lawrence published his paper in an obscure journal. But the obscure journal was Journal of Atmospheric Sciences, which is not obscure. I mean, it's a good journal, a respectable journal, and mathematicians don't read non-mathematical journal, so that's the origin for this time which has been lost. Here's another page of the paper where you see that he was ahead of his time discussing dynamics of one-dimensional maps. We will see that later. And then something happened. He was invited to some conference, and as usual he was not sending the title of his talk to the organizers, so the organizer had to create a title for him, and the organizer suggested this title for his talk: "Does the flap of a butterfly's wing in Brazil set off a tornado in Texas?" And just this sentence was so nice that it created in the general audience a big publicity, and it became famous as the butterfly effect. I think it would be very interesting to spend some time, but not today, trying to understand how a mathematical idea can percolate in the public audience. There's a very small number of ideas, of mathematical ideas, that can go to the mathematical audience. For example, this idea of sensitivity to initial condition was well known to Poincaré. Poincaré wrote wonderful pages almost containing the same concept. Almost. Hadamard had wonderful papers containing exactly the same concept, maybe 70 years earlier. But it was not possible to go into the general audience. How is it possible? Maybe just because of the wrong choice of words. I think choosing the right word, choosing the right title, even in mathematics, choosing the right titles for your papers is something very important. Because you have to be aware of the fact that most of your colleagues will only read the titles of your papers. So this is something you have to think about. Choosing titles, choosing the right word. And then all of a sudden it became a well-known idea in the general population, the concept of butterfly effect. It became famous in films, for example. And let me show you, I cannot resist. I typed butterfly effect on Google, not Google, on YouTube. And I want to show you what comes first. It's an reclam. This is what comes first on a small effect.
Line comes at you fast. Be ready with nationwide investments, retirement, insurance.
Nationwide is on your side.
So you see, really, this is number one. If you type butterfly effect, if you type Henri Poincaré, you don't have something like that. I can tell you. Okay. Anyway, let's go to some more precise mathematics now. I want to change gears and speak about something else. I think in this school you had courses on knot theory. I want to tell you something about knot theory. Maybe you explained that. But once again, knot theory came from physics. It's a wonderful story. I wish I had more time to explain it. But anyway, long time ago, in the middle of the 19th century, Helmholtz proved a theorem that fascinated Kelvin. The theorem is the conservation of the curl, I mean of the vorticity of a perfect fluid moving in space. You can see here a little film showing a the smoke of a cigar. And then Kelvin was, at the time, there was no theory of atomic theory. I mean, nobody knew about atoms. Everybody was looking for something like atoms. And Kelvin had the idea that maybe an atom could be a vortex in space, in the ether. And maybe the kind of atom that we have, oxygen or carbon or whatever, could be related to the shape of the vortex. And then he said to his friend, Tate, you should try to create a table of possible knots, and maybe we could find some kind of bijection between the knots and the chemical elements. That was just before Mendeleev, looking for some structure in the space of atoms. And Tate began, and he worked hard. And let me show you one page of one paper of Tate. He's writing papers with hundreds and hundreds of pictures of knots. And his idea was coming from physics, or chemistry in the case. Of course, this was a wrong idea. We know today that atom is something more, is different from that, but anyway, it's still an example where the interaction between mathematics and physics has been so fruitful that even though the idea was physically not correct, from the mathematical point of view, it created a very nice theory, not theory. And this not theory has been so interesting for mathematicians, but also for physicists, as you know. Okay, so what's the relation between knot theory and the Lorentz attractor? Well, one idea is this. If you pick again the Lorentz attractor that you can see here, inside it you have many periodic orbits. I'm showing some of these periodic orbits here. A periodic orbit is a curve that runs in the attractor and comes back to itself. When it comes back to itself, it creates a knot. So you could try to understand the structure of the Lorentz attractor by trying to understand the topology of the knots that are created by the periodic orbits. And so to speak, you see here numerically it's not so easy to find them, but here are some examples. And the general idea is that if you are clever enough to say something interesting enough on the topology of these knots, maybe you could think of the Lorentz attractor itself as being some kind of limit of its own periodic orbits, some kind of topological limit of its orbits. You see, here is a link consisting of maybe 5 or 10 periodic orbits, and the idea is that somehow one could approximate the attractor itself as a limit of knots. So the task is try to say something about these knots, and maybe you get as a reward some information about the Lorentz attractor. This has been studied by Williams, I mentioned earlier. So let me show you something. I show you on the screen an object called the Lorentz template. It is built out of 2 strips of paper. Each one of the 2 has a narrow side and a wide side. And they wrote, well, you can see it on the screen. You see, it's not quite a surface because along the middle interval, the vertical interval, on the left-hand side, you have 2 surfaces arriving, and on the right-hand side, you have some kind of a singular point. So it's not a surface, it's so-called a bunched surface. Now, the idea of Williams is that on this object, there is a dynamical system. Well, this is better. On this object, you have a dynamical system. Let me show it to you. You see, a point is moving along this branched surface and is coming back and back again, always on the vertical interval. And the trick is that if you take a parameter x for this vertical interval from 0 to 1, the first return map is x goes to 2x modulo 1. So every point on the vertical interval moves along this dynamical system and comes back to the vertical interval after multiplication by 2 modulo 1. So the point is moving, going left or right according to whether it is bigger or less than 1/2. So if you have such a picture, then you can look for periodic orbits. A periodic orbit will be a point which comes back to itself after a finite number of multiplication by 2. So here are some examples. You have here the point 1/3. 1/3 multiplied by 2 is 2/3, multiplied by 2 is 4/3, but 4/3 is 1/3, modulo 1. So you see, for each rational number with odd denominator, you have a periodic orbit for this picture. Now, the belief of Williams was that this picture is the correct picture for the Lorentz attractor. Combinatorically, the knots that we get in this way are exactly the knots that we get in the Lorentz attractor. So that's a belief. So he created the concept of geometric Lorentz attractor, which is something which is not necessarily related to the original differential equation, but which is governed by this template. And he proved many interesting theorems about this geometric Lorentz attractor. But it remained a question for a long time. Is this picture describing or not the original differential equation of Lorentz? And it's a rather new theorem due to Tucker, 2002. Tucker proved that indeed the combinatorical model proposed by Williams is indeed a good model for the original Lorentz equation. So indeed the picture that you have here with the description of periodic orbits as periodic points of the multiplication by 2 is correct. So if you want to describe the topology of periodic orbits of the Lorentz attractor, it is enough to look at the knots that you get for each rational point between 0 and 1, multiplying by 2, producing this way, you get a knot. So using this combinatorical description of the periodic orbits of the Lorentz attractor, Williams and Biermann were able to prove remarkable theorems about knots that appear as periodic orbits in the Lorentz attractor. And if you don't understand all these words, don't worry. The only point I want to mention is that to be a knot appearing in the Lorentz attractor is a very, very strong condition. Most knots are not periodic orbits of the Lorentz attractor. So I put here some statements. Lorentz knots are fibered. They have a positive signature. Oh, not curvature, signature. They have a positive. Sorry. They have a positive signature. They are prime. There is an infinite number of Lorentz knots, and each given knot appears only a finite number of times in the Lorentz attractor. Okay, so here's an example. Using their paper, you can check whether or not a given knot appears or not. So for example, I did the computation myself, or my computer did the computation. I took all the knots with less than 13 crossings. You have 1,700,000, well, this big number of knots, of possible knots that you can find on the internet. You have tables of knots. And among these 1,700,000 knots, only 20 are Lorentz knots. Only 20 of them appear as periodic orbits of the Lorentz attractor. Here you can see 8 knots, which are the only 8 Lorentz knots among the 250 knots with less than 10 crossings. So indeed, to be a Lorentz knot is a very, very strong condition. So Bierman and Williams were very happy with that because it tells you something about the dynamics of the Lorentz attractor. The periodic orbits have a very special topology.
What about group of knots?
You mean links? What do you mean by group of knots?
Fundamental group of complement.
Oh,
Fundamental group.
the fundamental group of the complement is, first of all, you know, I said the knots are fibered. To be fibered, is a property of the group of the knot. So it gives you a very strong condition. There's a homomorphism onto Z such that the kernel is finitely generated, which is a very strong condition for a group. That's one condition. Okay, so I propose to change gears again. So let's forget about Lorentz attractor and let us discuss some other dynamical system which is also very famous and which a priori has nothing to do with the Lorentz attractor. And what I want to discuss today is this new dynamical system, and the main result of this talk will be that this new dynamical system and the Lorentz attractor are somehow the same. So I want to discuss a very famous dynamical system called the modular flow, and I will show you first of all what it is, and then I will tell you that this modular flow turns out to be the same as the Lorentz attractor for some reason that I don't quite understand. So I want to begin by some preliminary discussion about the space of lattices. As you know, a lattice lambda is a subgroup of R2 which is discrete and which is isomorphic to Z2. Such a lattice has an area, or I should say a co-area, which is the area of a fundamental domain. And the claim is that one can think of the homogeneous space SL2R modulo SL2Z as either the space of lattices of area 1 in the plane, or as the unit tangent bundle to the Poincaré disk. I should say the Lobachevsky disk here. Okay?
The Lobachevsky plane.
The Lobachevsky plane, the Poincaré disk and Lobachevsky plane. Okay, okay. Sorry. Okay, so why is it so? That's very easy. If you have a matrix in SL2R, and a lattice in R2, you can just transform the lattice by the matrix. It's another lattice. So this describes an action of SL2R on the space of lattices, this action is transitive, and the stabilizer of the standard lattice Z2 is SL2Z. So indeed, the space of lattices of area 1 is indeed the homogeneous space SL2R modulo SL2Z. Now, if you want to think about the Poincaré disk or the Lobachevsky plane, you just the same way. PSL2R, not SL2R. PSL2R is the group of orientation preserving isometries of the Poincaré disk. It's acting on the Poincaré on the unit tangent bundle to the Poincaré disk, and you have this identification again. Okay. Now, on this space, the space of lattices, you have a very nice topology. It is something that has been known for years, maybe centuries, I don't know, that the space of lattices of area 1 in the plane, SL2R modulo SL2Z, turns out to be homeomorphic to the complement of the trefoil knot in the 3 sphere. One of the ways to prove it, there are many ways to do it, one of the ways to do it is to use standard methods from number theory. If you have a lattice lambda in C or in R2, you can define several numbers. One is called G2 and the other one is called G3.
G sub 3, not.
That's G sub 3, not G sub 2. I did that yesterday night, so okay. G sub 3. So G2 is the sum over all elements in the lattice which are not 0 of omega to the minus 4 with a coefficient 60 in front of it. And G3, not G2, is the sum of the omega to the minus 6 over all elements of the lattice which are not 0. And the main theorem, maybe due to Jacobi, I think, or I don't know, is that indeed, if you associate to a lattice lambda these two numbers, G2 and G3, well, these two numbers characterize the lattice. G2 and G3 characterize the lattice completely, and the pair of complex number G2, G3 can be any complex number satisfying the inequality that G2 cubed should not be equal to 27 G3 squared. So you can identify the space of lattices as the space of complex numbers, of pairs of complex numbers, such that G2 cubed is not equal to 27 G3 squared. So here's a picture in the real domain. So this is a picture of C2. The vertical axis, the green axis, is G2 is equal to 0. The horizontal axis is G3 is equal to 0. And one of these one of these cubics, G2 cubed is equal to 27 G3 squared, represents the forbidden locus where corresponding to non-existent lattices. Now, if we want to look at lattices of area 1, we have to normalize that by intersecting with a sphere around the origin. And this sphere will intersect the picture exactly on the space of lattices. So let me show you again a picture that a film that I showed already yesterday to illustrate the situation in the space of lattices. I remind you that for any lattice lambda, you can define G2 cubed minus 27 G3 squared, which is traditionally denoted by delta. It's a complex number, which is not 0. And you can associate to each lattice the argument of this complex number. This provides a map from the space of lattice to the circle. It is a fibration. And the fibers are surfaces. The surfaces that you saw the other day, they are surfaces whose boundaries are the given knot. And in the same way, there is an action of the circle on the space of lattices just by rotation. If you have a lattice, you can let it rotate, another lattice. So each time you have a point in the space of lattices, you have a circle of points. This action is free with two exceptions. A square can be rotated by 90 degrees, it's the same square, and an equilateral triangle can be rotated by 120 degrees, it's again the same lattice. So here's the picture again. So this represents the space of lattices having delta a real number. Then I will move, showing you the fibers of the vibration. So these are the pre-images of the map argument of delta. And then you see several fibers, as I explained the other day. And finally, I will show the circles corresponding to the action of the circle that you will see arriving soon. Oh, no, you will not see it. Anyway, so this is a picture of the space on which there will be a dynamical system, the modular flow. Now, what is the modular flow? The modular flow is something very easy. If you have a lattice in the plane, you can transform this lattice by a diagonal matrix, exponential t 0, 0, exponential minus t, it's another lattice. So each time you have a lattice, you can flow it by this one parameter group of transformations. And you get a curve in the space of lattices. This is the dynamical system we want to look at. Starting from each point in the space of lattices, there's a curve of lattices going out of it. This is a very famous dynamical system. This is the standard example of an ortho flow. Not standard because SL2R modulo SL2Z is not compact, but it is anyway the standard example of hyperbolic dynamical system acting on a three manifold. So let me show you some orbits. So let me explain what it is. The yellow knot is a trefoil knot. The space of lattices is the complement of this yellow knot. Now I pick a small ball that you can see in the middle of the cross. This is a point in the space of lattices, so it's a lattice. Then you can see two curves emanating from this point, a red one and a green one. These are the stable and unstable direction. And also flows come with stable and unstable direction. So one should be able to draw the unstable curves and the stable curve. So in a second, when I will push the button, the dynamics will start. And you will see the stable contracted and the unstable expanding. It will start during a few seconds, then come back, and then the dynamics will move backward. So you will see the opposite phenomenon. So here's the dynamics. Oops. Okay, so you can see here that the green almost disappeared. No more green. The green collapsed so much that you don't see it again. And the red expanded. And negatively, the red disappears and the green is expanding. You can see how crazy the dynamics is. You know, if you pick a point at random, you see these kind of pictures. It's chaos. It's the simplest example of a chaotic dynamical system. So again, in red, you see the stable manifolds, and in green, you see the unstable manifolds, and in blue, you see the one trajectory. Okay, so let's try to understand the periodic orbits of the modular flow. Well, periodic orbits of the modular flow have been studied for many years. Well, it's fair to say that the first to study it is Gauss. When Gauss studied quadratic forms with integral coefficients, well, of course he was not using this terminology, but he was indeed working with periodic orbits of the modular flow. So for today, let me just mention something very simple, that one can parameterize. There is one periodic orbit for the modular flow for each conjugacy class of hyperbolic element in PSL2Z. So why is it so? Well, what does that mean to be periodic? The dynamics is acting on SL2R modulo SL2Z. So a fixed point or periodic point for the dynamics is just solving the equation exponential t 0, 0, exponential minus t, p is equal to p modulo SL2Z. So there should exist some matrix A in SL2Z such that exponential t 0, 0, exponential minus t is equal to p a p inverse. Now that's very easy. If you give me a matrix in SL2Z, in PSL2Z, hyperbolic, it's a 2 by 2 matrix. Then you give it to me and you ask me, could you please diagonalize it? This is the kind of thing I can do. I think I can do that. Okay, so when I diagonalize it, I find a matrix P satisfying that. So I found a periodic point. Conversely, if I find a periodic point, I solve this equation, which means that I have found a diagonalization for the matrix A. In other words, each matrix A corresponds to a unique periodic orbit, and a periodic orbit corresponds to a unique conjugacy class of matrix A. So there is a dictionary between periodic orbits and conjugacy classes of matrices in PSL2Z, which is a fascinating subject: continuous fractions, ideals in quadratic fields, and so on and so forth. So what I like in this is that you can thus associate to each matrix in SL2Z a periodic orbit. But the periodic orbit is a curve in space, hence is a knot. Consequently, for each conjugacy class in PSL2Z, there is a canonically defined knot in the complement of the trefoil knot. And the question I want to discuss today are, what kind of knots do we get? And question, can we compute the linking number of these knots with the trefoil knot as a function of the matrix? So that are the two questions I want to describe today. So I hope you agree with me that for each matrix there is a canonically defined associated knot. This knot lies in the complement of trefoil knot, so one wishes to compute the linking number. Okay, so before I give you the answer, let me show you some film. So for each matrix, I can compute everything. I have the matrix, I can diagonalize it, I can find the periodic orbit, I can draw the picture. So here are a few examples. Let me begin by the most trivial example, the famous 1, 1, 1, 2. And you can see that this situation is kind of boring, because for the 2, 1, 1, 1 matrix, the periodic orbit that we get is a stupid unknot lying in the middle of the picture. So you see, I was disappointed by this stupid answer. Then you take a more complicated matrix, like for example 1, 2, 1, 3, and here's the corresponding periodic orbit. It's still a trivial knot, but located in a different way with respect to the trefoil knot. Here's the first case where you see the red knot is a trefoil knot. another one, and then it's a torus knot. So each matrix gives you a knot, and you can look for which knot it is in the table. And it's rather easy to compute. This one has been chosen at random. I don't know which knot it is, but I can tell you it's non-trivial. I can compute the signature, for example. Okay, so that's the two main goals. How can I compute the linking number of this knot as a function of the matrix? And what are these knots? So here's the theorem. The linking number of the knot between the periodic orbit associated to a matrix A and the trefoil knot is given by what I call the Rademacher function. Of course, I will remind you what Rademacher function is, and one of the main difficulties is that it is a function which has so many names that it's difficult to find a name. So I think maybe the best name is Rademacher, but maybe it's unfair, I don't know. So let me recall what Rademacher function is. It's something very well known in number theory. There is one function that has been studied by many people, and even in a paper by Atiyah claims that this is the most famous function in mathematics. Well, I think maybe exponential of sine are maybe more known, but anyway. Okay, this is this function defined in the upper half space, eta. Eta of tau is given by this infinite product, exponential of 2i pi divided by 12, infinite product, blah, blah, blah. The main point of this function is that it is a modular function of weight 24, which means that when you transform it by the action of PSL to Z, it is not invariant, but its 24th power is kind of invariant with this modular factor C tau plus D to the 12th power. This is the main property of this function. Now, the second main property is that obviously this function does not vanish. Look, by the definition, it's a product of non-zero numbers. Now, since eta is a function on the upper half space that does not vanish, and since the upper half space is simply connected, it does make sense to take a log of it. So you take log on both sides, and you get 24 times log of eta at the point a tau plus b, c tau plus blah 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 is equal to 24 blah up to a constant multiple of 2i pi. Because of course, if two numbers are okay, because the log is determined up to a multiple of 2i pi. Anyway, you get this formula, the last formula, plus 2i pi times some integer, r of a. R of a is a function canonically defined on SL2Z that I call the Rademacher function. Well, maybe I should call it the Riemann function, because when Dirichlet, was it Dirichlet? Yeah, I think when Dirichlet was asked to look at the papers of Riemann after his death, he found a manuscript in which Riemann was asking the question, well, giving this definition essentially, and asking the question, how do I compute? If you give me a 2 by 2 matrix, A, B, C, D, how do I compute R? And Dirichlet found, made some comments about this paper of manuscript of Riemann, and finally he created Dirichlet sums for that, and it's a long story. I mean, I could spend hours on this topic. Anyway, it's a fascinating function defined on SL2Z that appears everywhere. And yep.
The logarithmic derivative of eta is the Eisenstein series E2, right?
Yeah.
So this is E2 times eta, actually.
Логарифм, конечно, натуральный, понимаете.
So that's the
Okay. Before I prove it, let me show you. No. Let me prove it. Let me prove that this indeed, the Rademacher function is indeed the linking number with our periodic orbit. Well, I can prove it waving my hands easily. There's the theorem of Jacobi that says that delta, you remember delta is G2 cube, etc., minus 27, etc. Delta is equal to eta to the 24 with some constant in front of it. Now, what is the trefoil knot? Trefoil knot is delta is equal to 0. So what is a linking number with delta? Is, so to speak, the number of times you turn around the trefoil knot. But turning around the trefoil knot is essentially looking at the argument of delta. The argument, you count how many times you rotate around 0. But the argument of delta is the argument of 24 times the argument of eta. But the argument of a complex number is essentially its log. Okay? That's it. The definition of R that you have here involves log of eta. And log of eta is essentially the argument of delta. If you just, you have enough to finish the proof yourself. So, let me show you a picture of some example. You have here a knot. It's moving in space, and from time to time it intersects the Seifert surface. Delta is a real number. So, it could intersect positively or negatively. Here you see it intersects twice, so the linking number is 2. This means that when you go around the knot, the delta will rotate twice around the origin. So again, what you see with your eyes is just delta is log eta. So for every knot, you can compute the linking number very explicitly using this Rademacher function. Okay, now theorem. Oops. I think I hope you guessed the theorem. Theorem. Lorentz knots appearing in the Lorentz attractor are the same as the modular knots appearing in the modular flow. So these two dynamical systems coming from different origins, after all, they have the same periodic orbits. When I say the same periodic orbits, of course they are not the same. Each periodic orbit of one is isotopic to a periodic orbit of the other one. So they are somehow related, even though they are not the same. There's a bijection between the periodic orbits of the first one and the periodic orbit of the second one that preserves the topology. That's what I want to explain to you. So I have...
Oh, you have at least 20 minutes.
Okay. So this is the main theorem. Theorem, the modular knots and the Lorentz knots are the same. Up to isotopy, of course. So maybe I should...
I will ask you the same question that I asked in Toulouse.
Yes?
Isotopic as as knots in R3 or isotopic as what?
Isotopics are not in R3, yes.
In the complement to the tree.
Well, the trefoil knot appears in the space of lattices, but there is no obvious trefoil knot in the Lorentz attractor.
Ah, I see.
Okay, but it is true that if you give me the Lorentz attractor, I can draw. You will see it in a moment. A Lorentz knot. I can draw a trefoil knot outside of it. That looks kind of artificial, and it is a fact that periodic orbits of the Lorentz attractor and periodic orbits of the modular flow are isotopic in the complements of their trefoil knots respectively. But the second one is kind of artificial. Okay, so here's a very rough idea of the proof. I told you that the modular flow, that the space of lattices can be seen as the unit tangent bundle to the quotient of the Poincare disk by PSL to Z. When one thinks of the space of lattices as in this way, the modular flow is nothing more than the geodesic flow. In other words, what you saw here is nothing more than pictures of periodic geodesics on the modular surface. The modular surface is the quotient of the Poincare disk by PSL to Z, and many of you have seen this picture with a cusp, two singular points, and a fundamental domain that most of you know for the action of PSL to Z acting on the upper half space. So what we want to understand is the behavior of geodesic, closed geodesics on this modular surface. So the trick is this. The modular surface has a cusp, has a very thin end. What you do is you open the cusp. By opening the cusp, I mean you replace it by a funnel. You open the cusp in the So you replace the action of PSL to Z, the standard action of PSL to Z on the upper half space, by a new one. But the new one is still acting discretely, properly. The quotient now has infinite volume. It had a cusp, you open the cusp to make a funnel. Okay, I have to say that if you don't understand this is, I'm guilty, you are not. I mean, because I see your eyes open, I'm going too fast, I'm sorry. So it's kind of normal if you don't understand. So you open the cusp. This gives a family, let's say, with one parameter of manifold with negative curvature. When the parameter is 0, it's the modular surface. When the parameter is 1, it's a funnel. And what's happening is that when you open the cusp to produce this funnel, the so-called convex core is collapsing in the neighborhood of this interval. So when the funnel is very much opened, you see a picture something like that. You have something like that. The new surface has a huge funnel, and geodesics are trapped in a very thin neighborhood of this one-dimensional object. Okay. Now, the next observation is that everything has negative curvature. And if you have a one-parameter family of manifolds with negative curvature, you can follow by continuity any periodic orbit. Any periodic orbit can be followed continuously. So the trick is this. You will start with the periodic orbit for the modular surface, maybe very complicated, and you will open gradually the cusp in such a way that the periodic orbit will move slowly downwards and will approximate this very thin region. And the point is that after you do that, the approximation is so good that everything will be in a tiny neighborhood of this, which will look like a template. So let me show you on the film. Okay, oops. How do I stop that? Okay, this again is the picture of the space of lattices. Again, the complement of the yellow trefoil knot is the space of lattices. What you see in the middle is a big circle and a diameter. I can tell you, the big circle consists of all square lattices. Square lattices depend on one parameter, its orientation. The set of square lattices is a circle. This diameter is the space of rhombuses. Rhombus is a rhombus. Let's say, but with horizontal diagonal. Okay, it's a one-parameter family. So you have this one-dimensional object, which, from the differential geometric point of view, corresponds to the unit tangent bundle to the. In upper half space, you have this famous picture. You have this invariant tree. It's the unit tangent bundle to the tree. It's one-dimensional object. Now I will take a slight perturbation of this object in the stable direction to produce what I call the modular template. Oops. Something wrong. Okay, here it is. This is a small neighborhood, a stable neighborhood of the one-dimensional object I described. This is a two-dimensional object, a branched surface, sitting inside the space of lattices. And then I take one of these modular knots, for example, associated to the matrix you have seen. The knot is not related to the template, a priori. And then I do this deformation I mentioned. I open the cusp. And you can see that the knot is deforming gradually and will deposit onto the template. So if you wait long enough, the knot will deform and will converge to a Lorentz knot. So for every matrix you can do the same picture. You have this knot, you don't know what it is a priori. You open the cusp and the motion that is explicitly given by formulas that I had to write down to produce the film will project by an isotopy the knot onto the template, so that after this isotopy the knot looks like a modular Lorentz knot. This gives the perfect dictionary between the Lorentz knots and the modular knots. Now you can ask me, given a modular knot, you put it in Lorentz form, it will go left, right, right, left, left, right. How do I guess the sequence of right and left? Of course, it's related to continuous fraction. You can see from the continuous fraction expansion or the expression of the word in the group PSL2Z, you can see the list of right and left just explicitly. So you see this picture comes from the modular flow and looks like the picture that you have seen at the beginning of the Lorentz attractor. Okay, now of course I should give more details on that, but I have no time to do that. What I want to finish with is something which is kind of unrelated, but I like very much to show because it's I think beautiful. Is the same picture not for geodesic flow but for horocyclic flow. So the horocyclic flow is the same, so to speak, as the modular flow, but instead of multiplying by a diagonal matrix, you multiply by unipotent matrix 1, T, 0, 1. It gives you a dynamical system, again acting on the space of lattices. And it is a fact that this dynamical system has periodic orbits. If you take the lattice lambda to be z squared, you can see that the lattice is periodic with period 1. But if you transform this lattice by the geodesic flow, you get a new lattice which is still periodic, but now the period is exponential of 2s. In other words, the horocyclic flow has a family of periodic orbits depending on one parameter. Those are not very difficult to understand. They are just those closed horocycles that you see in the cusp. Very small here and getting bigger and bigger and bigger and bigger and then complicated, but always closed. So I want to show you now is a film showing the behavior of this one parameter family of periodic orbits as S will evolve. When S is very negative, it is a trivial knot, stupid knot, going around the cusp, very far away. But when it's very positive, it will be a much longer knot. And the fact is that these knots, depending on S, will tend to occupy all space. It is an old theorem of Dany that to the limit, this family of knots will equidistribute in the complement of trefoil knot. So I'm going to show you a family of knots depending on one parameter, filling space in an ergodic way, so to speak. And I like to say that there is a famous or not so famous theorem, I don't know who proved it, probably Ziegel, giving an equivalent statement to Riemann hypothesis, according to which the velocity of convergence of these closed orbits to the full space is equivalent to Riemann hypothesis. I don't want to give more than that. Let me show you the picture, and that will be the end. So, okay, so here you see the small green curve, the small horocycle, trivial knot, and then it's growing slowly, always a trivial knot, and the length is now increasing, and these knots will get crazy and will try to fill space as much as they can. They are periodic orbits of the horocyclic flow. And again, if you take a smooth function in space, and if you integrate this smooth function on the green lines, it should converge to the integral of the function on space, and the difference is equivalent to Riemann hypothesis again. It's kind of crazy again. Huh?
trivial knot all the time.
This is always an isotopy. All these knots are the same. Actually, they are trivial knots. Linking once with the here's the M. Okay, thank you very much.